Hello students, welcome back. Let's start with an interesting thought. If differentiation helps us find the slope of a curve at a single point, what about the opposite idea? Can we measure the total area under that curve instead? That's where integral calculus steps in. Differential calculus, as you know, deals with tangent lines and slopes, the rate of change. But integral calculus is about accumulation, the big picture. And historically, the great mathematician Leibniz gave us the beautiful notations of integrals that we still use today. So think of it this way, differentiation zooms into a single point, while integration zooms out to capture the whole region beneath a curve. Now let's ask the first big question. If we are given the derivative of a function, say f dash of x, can we reverse the process and find the original function f of x? Mathematically, this means finding a function f of x such that df by dx equals f of x. These are what we call antiderivatives. The second big question is, how do we calculate the area under the curve y equals f of x between 2 points on the x-axis? And here comes the beauty. The first problem gives rise to indefinite integrals, while the second gives rise to definite integrals. So in short, integration is about reversing differentiation and calculating areas at the same time. Let's start with indefinite integrals, also called antiderivatives. The notation is integral of f of x dx equals f of x plus c. Here c is the constant of integration because adding any constant doesn't change the derivative. This means that all functions differing only by a constant belong to the same family of antiderivatives. For example, since derivative of x squared is 2x, we can write integral of 2x dx equals x squared plus c. Now let's move to definite integrals. Unlike indefinite integrals that give us functions, a definite integral gives us a number, the signed area under the curve. So the notation is integral from a to b of f of x dx. Formally, this is defined as the limit of a sum of rectangles under the curve, limit as in tends to infinity of the summation of f of x I into delta x. If the curve is above the x-axis, the area counts as positive. If it is below, it counts as negative. This way, definite integrals let us measure accumulation over an interval, not just find the family of functions. Here comes the magical connection, the Fundamental Theorem of Calculus. It tells us that differentiation and integration are inverse processes. If f dash of x equals f of x, then integral from a to b of f of x dx equals f of b minus f of a. This is powerful because instead of computing limits of sums, we can simply find an antiderivative and apply the upper and lower limits. This theorem ties indefinite and definite integrals into one unified idea. Let's solve an example step by step. Question: find the area under y equals x squared from x equals 0 to x equals 2. Step 1. Write the integral from 0 to 2 of x squared dx. Step 2. Find the antiderivative. Integral of x squared dx equals x cubed by 3 plus c. Step 3. Apply the limits. Put 2 in place of x. 2 cubed divided by 3 equals 8 by 3. At 0, it becomes 0. Subtracting gives 8 by 3 square units. So, the total area is 8 by 3. Notice how smooth it is once you know the antiderivative. Integration is not just theory, it's everywhere. In kinematics, integrating velocity gives displacement and integrating acceleration gives velocity. In economics, integrals help calculate consumer surplus, producer surplus, and revenue. In probability, integration defines distribution functions and expected values. And in engineering, we use integrals to calculate work, volumes of liquids, and even heat transfer. So integration is the mathematics of accumulation across every field you can imagine. So, let's recap. Differential calculus handles slopes and rates of change, while integral calculus handles accumulation and areas. We studied two main problems: recovering a function from its derivative and finding area under a curve. That led to indefinite integrals and definite integrals. We saw that indefinite integrals give families of functions with a constant of integration, while definite integrals give exact numerical values. And the fundamental theorem of calculus beautifully links the two. That's the introduction to integrals, the art of accumulation in mathematics. In the next video, we'll explore the basic techniques of integration and learn how to actually compute different types of integrals step by step. See you there.